This video is part of the MCAT Chemistry video course. Subscribe if you'd like notifications about the release of future MCAT videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to finish our discussion about electron configuration, and we'll go over how to actually fill in the configuration, how to make orbital diagrams, and then how all of that connects to the periodic table. I recommend going and watching part 1 unless you feel really comfortable about electron configurations in the first place. The first thing that we're going to go over is the order in which we fill the subshells. And remember that electrons do reside within orbitals, but we will talk more about that when we do orbital diagrams. So right now, all we're focusing on is the order of subshells that we put the electrons in. And you want to make sure you're comfortable with this chart on the left, where we have the subshells that are contained within each energy level. And then you also want to be comfortable with this first bullet point, that we're going to fill these subshells in order of increasing energy. And you may be tempted to think that increasing energy would start with 1s, and then go 2s, and then be 2p, and then be 3s, and then be 3p, and then be 3d, and then 4s, and then so on. But it's actually not going to be that. So that is not the order in which we fill it. The order in which we fill it is based off of this chart with the arrows that we see here in the middle. And notice that all this chart is so mentally take away the arrows, and all this chart is listing this table here with the energy level and the subshells that they contain. So that's all the chart is. We don't ever go past F, and that's just because we're never going to have enough electrons to do that. Theoretically, you totally could keep adding after F, but there's just no reason to do that because you're never going to need it. And then after you make this table, starting at the top, just draw diagonally all the way through. So I'm just going to trace these arrows just so you can get the idea. Just the first 3 or 4 arrows. And then what you want to do is you want to think about if you were to draw that arrow, what order did you go through those subshells? And so the order would be 1s, 2s, and then that third arrow goes through 2p first, and then it goes through 3s. And then the fourth arrow goes through 3p first, and then it goes through 4s. And so we don't hit 3d until after 4s because that blue arrow here, that fourth arrow, has to go through 4s first, and then the next arrow goes through 3d, 4p, 5s. So it'll be 4s, and then 3d, and then 4p, and then 5s, and then you just keep going with that chart and with those arrows. And you have to completely fill a subshell before you move on to the next subshell. So 1s would need 2 electrons in it before we would start putting any electrons in 2s. And then something like 2p would need 6 electrons in it before you start putting something in 3s. And then, so that leads us to this other way that we can write our configurations, where we have a second number. So look at this one, it has 1s2. And that second number is telling you how many electrons are in that subshell. So if we just rewrite our order up here, we already have it written down here, and that would just have these numbers written after it: 1s2, 2s2, 2p6, 3s2, and that second number, again, that's just telling you how many electrons there are. And normally you're going to see those numbers written kind of like a superscript. And so just get used to seeing them either just written right after the letter or as a superscript. Either way, you're going to be totally fine. So real quick, let's just do an example of nitrogen's electron configuration, and we're going to do it this notation down here with the 2 numbers, with the second number representing how many electrons there are. So for nitrogen, there are 7 electrons, and we get that number by looking at the periodic table. It has an atomic number of 7. That means that there's 7 protons, and then anytime you're just grabbing an element from the periodic table, you're just going to assume it's a neutral element. So if it's neutral, the number of electrons cancel out the number of protons. So there's also 7 electrons. And then we just start with our chart up here to know our order. So our first one will be 1s, and then there will be 2 electrons in that one. And then we will do 2s. There's going to be 2 electrons in that one, and we only have 3 electrons remaining. Our next arrow goes through 2p. So then we have 2p, but there's only 3 electrons left. So it would be 2p3. So that's your electron configuration for nitrogen. Orbital diagrams are the next part of this, and they're just a way to better visually represent electron configurations and they give us a better idea about filling the orbitals within the subshells. So we're still filling these in the exact same order that we just discussed. It's just now we've added these lines, and each one of these lines represents one orbital. And sometimes you're going to see it written like this, where you have it written vertically, and as you go up, the energy level goes up. So you can see it written like that. Other times they might write something like 1s there, and then they might write the p subshells over to the right. So you have like 2p, and they put it over here on the right, and then they go back to the left to do the 3s, and then they'll put the 3p over on the right again. And it's just different ways of writing it. You also could even see some where they just write it horizontally. So 1s, and then just right next to it 2s, and then put 2p right next to that one. The horizontally is probably the most likely one that you're going to see on the test. And then sometimes instead of lines, they might actually do boxes. So any one of those is totally fine. They all mean the same thing. And then, of course, any one of these could continue way past 3p or whatever we've written, and we'll just go for as big as the electron configuration is for that element. And so let's just start working on this one over here and just start filling this out, because there are a couple rules that we need to point out that just kind of make more sense as you're filling it out. So the first one is that when you fill these out, you're going to use arrows to represent one electron. So on 1s, we're going to put an arrow, and it's like a half arrow, and sometimes you may see a full arrow that just points up. But the point is that that line points up, and what that tells you is what's called the magnetic spin. So this is, if you watch part 1 of the electron configurations, we go over quantum numbers. We left out one quantum number called the magnetic spin, and this is what magnetic spin is. It's what direction this arrow is pointing, and what it represents about the electron is the direction that the electron is orbiting, pretty much. So when you have a half up arrow, that's your magnetic spin, and the letter for magnetic spin is ms. So ms will equal plus 1/2 for up arrows, and then for down arrows, ms will equal negative 1/2. So that first electron that we placed, that is a plus 1/2 magnetic spin. And then the other electron that goes into that 1s orbital will have to be down. So it'll have to be negative 1/2. And you can never have two electrons that have the same spin in the same orbital. That's the Pauli exclusion principle, where two electrons cannot have all of the same quantum numbers. And if you had two electrons that are in the same orbital and then they have the same spin, every one of their quantum numbers would be the same, and that violates the Pauli exclusion principle, and you can't have that happen. So just remember opposite spins anytime you have two electrons that are in an orbital. So next we'll fill the 2s. That would be the exact same. And then we move on to 2p, and here's where we run into one of our other really important rules. And this rule is that you cannot have two electrons that are in one orbital until every orbital in a subshell has at least one electron. So we're working in subshell P. Every orbital in subshell P needs one electron before any of those orbitals can have two. And this would only happen if you have enough electrons that you're going to need to be doubling up. So let's just pretend we have an element that has a lot of electrons, and we're going to be going way past 2p. But first, you would want to fill it out just like this in this order. So place one in each orbital first, and then you start to double up. And then after you double up and every orbital has two, then you move on to 3s. And then let's say that we have an element that ends with 3p4. So it's going to have 4 electrons that are in the 3p subshell. So we would do one electron in each orbital, and we only have one remaining electron, and we would just place it in that first orbital with the opposite spin. So real quick, let's just do a orbital diagram for nitrogen and then one for oxygen. So we'll just write it over here. So nitrogen has 7 electrons. Oxygen has 8 electrons. And first, what I would recommend is always just write out your electron configuration before you start with the orbital diagram. So 7 electrons, we would go 1s, 2, 2s, 2, and then 2p. You'd have 3 remaining, so 2p3. For 8 electrons, don't even worry about rewriting the whole electron configuration. You already know what nitrogen's is. Oxygen just has one more. So it's 1s2, 2s2, and then 2p4. It's just going to be one more. And now just write out your orbital diagram. So write out the subshells that you know are going to have electrons in them. So 1s with a line, 2s with a line, and then 2p needs 3 lines because it has 3 orbitals. And then just start placing your electrons. Start with the lowest energy. So 1s is filled, 2s is filled. That gives us 3 remaining. And then we just put 1 electron in each orbital. And now do the same thing for oxygen. So 1s, 2s, and then that one also ends with 2p. The 1s is filled, the 2s is filled, and then the 2p, we start by putting 1 electron in each orbital. We have 1 electron remaining. So in that first orbital, we double up. And that would be the full orbital diagrams for nitrogen and oxygen. The last thing that we're going to do is look at how the periodic table is organized in terms of electron configuration, which is going to lead us right into noble gas configurations. But we're going to fill in this periodic table with the final part of the electron configuration for each element. So remember, we just did nitrogen and oxygen, and just click back in that video to see how those ended. But nitrogen, the last part of that electron configuration was 2p3. And then oxygen, the last part was 2p4. So for nitrogen and oxygen, those two things are going to be what we're going to put in this periodic table. So again, it's just the ending of each of these elements' electron configurations. And starting with hydrogen on the top, we're just going to start there and just work our way through. So hydrogen only has 1 electron, so that's going to be 1s1. And remember that the number of electrons that we're saying each of these elements have is assuming this is a neutral element. So it's basically just the atomic number, tells us the number of protons, and then the number of electrons are going to be equal because we're assuming that these are neutral. So after hydrogen, we move over to the top right. We have 2 electrons, so that's going to be 1s2. And every time that we go up 1 atomic number, just 1 more electron. And we're just following that chart that we did in the very beginning of the video. So after the 1s is filled, we have 2s1, and then we have 2s2. Moving over to the right, we have 2p1, 2p2, 2p3, 2p4 through 2p6. And I'm just going to fill in a couple more of these, and then I will have the rest of the periodic table kind of have the rest of the answers filled in there, and then we'll go over how this is organized. But what I would recommend is just keep filling this out yourself until you are sure that you see what pattern is emerging here. But we're just filling in that third row just like we did the second row. And again, we go all the way to P6. This fourth row is the last one that I'm going to start filling out because it starts to get into the D subshell, which can be slightly confusing. So if you keep filling up your electrons, you'll be on the 4s1, 4s2, and then remember we're using that chart with the arrows that go through it, and after 4s, it's 3d. So 3d1, 3d2, and remember that the D subshell has 5 orbitals and it holds 10 electrons, which is going to end on the far right here with 3d10. So I'm going to go and fill in the rest of this periodic table, but make sure that, or go ahead and try to fill it out yourself and then see if yours matches what mine is about to turn into. Hopefully your periodic table looks something like this, and now we're just going to go column by column, which in the periodic table, the columns are called groups. So we're going to go group by group and just point out how each of those groups has the same ending in their electron configuration. So group 1 is all S1, group 2 is all S2, and then let's just skip the D subshell for now, and then we'll look. We have P1, P2, P3, P4, P5, and P6. And so that leads us to, sometimes you will see this where we have, this is called the S block, and then over here we can call that the P block. And then that would leave the middle to be the D block. And let's just go over the D block right now. So starting with the first part, we do have D1, and then D2, D3, and now here's where, notice it is D5. And I have a mistake there at the bottom. That should be 6D5 right there. So 6D5. So notice how that is D5. And the explanation for this is not something that you really have to know, but to me, it's worth just going over because it's going to help you remember this exception. So the D subshell has 5 orbitals. And it's way more stable for the D subshell to have 1 electron in each orbital, which would make that D5, than it is to have 1 electron in 4 orbitals and then just be D4 with that 1 open orbital. And so what happens is the elements that are in what normally would be D4, or what you would expect to be D4, they're going to steal one of the electrons from the S subshell. Let's look at this 3D5 element right here, this first one, to kind of illustrate exactly what's happening. So normally, look here on the far right, to the right side of the table is where I'm going to write this. Normally, you would have expected that would be 4s2, 3d4. So that's kind of how you would think that electron configuration would go, because we'd completely fill up the 4s subshell before putting electrons into that 3d subshell. And again, that's just following that chart from part 1 of electron configuration. But then what happens, because of what we discussed with the D subshells right above the D block, is one of those electrons from the 4s is going to go into the 3d subshell. So then we end up with 4s1, 3d5. And that's the exact same thing that happens with every row beneath that one. So like 4d5, the one right underneath that one would be 5s1, 4d5. And then once you go to the right, so we have 3d5, that's in group 6. And remember, group numbers are the numbers right above. So if we go to group 7, that one's also 3d5, but then that one will be 4s2, 3d5. So that extra electron actually just refills the 4s, or the S subshell, to give you that complete S subshell again. And then after 3d5, we're back to normal. Once we do 3d6, 3d7, 3d8, and then once again, the same thing happens with group 11. And it's the same idea where the D subshell just gets so much more stable if it can have 2 electrons in each orbital, which would give you the 10 total electrons. And the same thing is happening where it's taking an electron from the S subshell. So your S subshell is actually going to have 1 less electron than you would normally expect. And it's going to go into the D subshell to give you a completely full D subshell. And if you Google an electron configuration periodic table, you're going to see that some of our numbers don't match, because there's actually some more exceptions, where I think maybe like 4d8 is actually 4d10 or something like that. Don't worry about those whatsoever. Those exceptions are not going to come up on the test. It is possible that the ones we talked about could come up, but the super special ones those will never come up. And then lastly, if you look at the bottom, we do have the F block down here. You don't need to worry too much about the F block. It's pretty much never going to come up. And then notice just how to the left of the F block, we have the 5D1 and 6D1. Again, don't really worry about the whole notation of this. Just know that if you have a periodic table where you're missing those 2 blocks there, down here by the F block is probably where they are. But don't worry too much about the F block. It's really rare that you'd ever have to work with an element in there. And that leads us to the last thing, which is noble gas configurations. So the noble gases are on the far right of the periodic table. And we can use these to basically make electron configurations go quicker. So on the bottom here, I have written the configuration for a few of these noble gases. So let's just start with helium. So remember, helium only has 2 electrons, so its electron configuration is really simple. It's just 1s2. And then if we look at lithium, lithium will be just 1 more electron than helium. So if we look at our chart, lithium's electron configuration would be 1s2 and then 2s1. But then what noble gas configuration allows us to do is, instead of putting 1s2, we can do, so this would be equal to helium in brackets and then 2s1. And so basically helium is pretty much like a variable that equals 1s2, because 1s2 is the configuration of helium. So it's like a replacement for that part of the electron configuration. And for something like helium, it really doesn't make sense to use it because it's so short already. But let's look at something like potassium. So the noble gas right before potassium is argon. And we're going to use our skills that we just talked about with using the periodic table to help you with electron configuration. So argon would end in P6, and it's the third row down. So it'd be 1, 2, 3 P6. So that's going to be the ending of argon. And then if you look at that chart, again, always reference that chart with those arrows. It would go 3p6 and then 4s. So potassium should end with 4s1. And so we could write the entire configuration of potassium, which I'll actually just do that really quickly. It's 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. And then the configuration for argon is already written down here. And notice the part of potassium's configuration that is equal to argon's is that entire section right there. So then instead of writing that, we can just write that potassium's electron configuration is argon in brackets and then 4s1. So it's just a really simple way of writing electron configurations that saves a lot of time of just writing things out. And we don't just have to use group 1 elements here. We could do this with any one of these elements. So if you did something like phosphorus, for instance, so look at where phosphorus is. The noble gas that's before phosphorus would be neon. And neon's ends with 2p6 because it's row 2 and then it's in the p6 column. So for phosphorus, we'll just go ahead and put the neon in brackets and then just follow your periodic table to see what would be next. So neon's up here. Next would be 3s. So we have neon and then 3s2 and then go all the way over and now we're in 3p. So 3p1, 3p2, 3p3 is where phosphorus is. So neon, 3s2, and then 3p3 would give you the configuration for phosphorus, the noble gas configuration. And you want to be really good with noble gas configurations and regular configurations. They might give you answer options that are in either one of these types of notations. So you just want to be comfortable with either one.